To all,
Good evening, sir.
then we will start.
Yes, sir, we can start, sir, now.
Okay. Now the screen is visible.
Yes, sir. Yes.
Okay. So today the topic is image statistics of remote sensing. इसमें क्या है कि डिफरेंट टाइप ऑफ जितना भी स्टैटिस्टिकल इंफॉर्मेशन है एंड डाटा है और जनरली इन द रिमोट सेंसिंग वी यूज द pixel and the in the different matrix level. So these data are
Sir, can you please mute PVS and Naidu, please?
okay. Can थोड़ा सा म्यूट कीजिए. Okay. Then different type of statistics involved in the remote sensing technology based on the different pixel level information. So every pixel in the satellite image have some reflectance value. If it is a 8-bit image, then 2 to the power 8, that is 256. From 0 to 55, there is a reflectance value. So these values are the information about the Earth surface reflectance value. So based on this value, we will estimate the different areas and different calculation of different areas and interpretation of different areas. So a lot of times some images are not correctly uh, uh, given the records. So different metrics and different mathematical calculations are there. So based on this calculation, we changes the different aspect of the satellite image for different purpose. So that's why it is very much important for the statistical analysis of different remote sensing data, and it is also very much important for the deep learning and machine learnings and AI tool which are used nowadays. So in the remote sensor detect terrain features by using the different reflected solar radiations in the optical range, and then heat emitted by the objects in thermal range, and backscatter energy which is in the microwave range. So different type of electromagnetic radiations are collected in different sensor. So these data and these values are calculated in the different statistical analysis for giving the different outputs. So images are the final product of remote sensing, and then can that can be microwave, panchromatic, that is black and white image, or multispectral, that is color image, and hyperspectral, more than 100 bands are there. And then image statistics involve the study of remotely sensed images and their statistical properties. So it is involved of the image and the statistical properties of the different pixels of the satellite image. So basically, in the image statistics, it calculates raster cell statistics because it is in the different row and column. So from one and multiple selected images and compute the statistical measurement of the images consisting of different histogram, mean, median, mode, then distributions, covariance, correlations. So a lot of time there is a different longitudinal and cover analysis and change detection. So when the time some distributions and covariance are needed. So making meaningful sense of the huge amount of remote sensing data require knowledge not just about the handling but its basic statistical properties. So we have to know some basic statistics related to the remote sensing. Uh, then we will calculate the different indexes and different other different result of this remote sensing technology. So some of the basic statistics are discuss now. Now there are two type of data, that is qualitatives and that is a quantitative data. So in qualitative data, that is a non-numerical information. So there is no name, one, two, three, or any numeric, which describes the characteristic, qualities, and some attributes of some features. So that is called as qualitative data. Example is one of the residential area, agriculture, forest area, and in the land use land cover. So this is a qualitative data. And quantitative, it gives the information that measures the express the number, like the distance of one object from a river or any forest area, and buffer analysis in the GIS, that is a quantitative data based information. Then level of measurements are there. So a lot of level of measurements are there, so which includes nominal data, which reference level and categories like green, red, blue of different color. So there is a nominal data. Then ordinal data, it is represent the levels or categories like different hierarchy like high school, graduation, post graduation, or literacy, illiterate, literate. So it is a hierarchical data. And then the interval data. So this is the third level of measurements, and it extends the characteristic of ordinal data by exhibiting equal interval between the values. So includes the temperature in Celsius or Fahrenheit. So it is a interval data. And then ratio data, that is the highest level of measurement, that is age, height, income, weight. This is just the statistical technique. So ratio data also on the basic description of statistics like regression, other advanced modeling techniques. So there are four level of measurement. Then population and samples. So lot of time in the GIS field we have to calculate different sample data for calculation of the entire population. So in the statistics, the population refers to the entire group of event or feature which can have the information, and sample is used for the small subset of the population. Suppose there is a forest area, and we have taken one of the sample of a particular 1 square kilometer, then calculated the different species, how much species are found in a per square kilometer. So this gives the some basic idea about the forest, that this forest has some this 20 or 50 type of different species are found. So it may be some wrong information, because entire forest area have not the same species are found. So this is one of the example. So sample data is very much important in the GIS work, in the remote sensing GIS work. So there's the uh, formula of the Slovin's formula, that is n is equal to n by 1 is to n into e square, where n is the sample size, small n is the sample size, and capital N is the population size, and e is the error tolerance. So how much error is there? So if you calculate sample size n by taking a population size of 10,000, so for example, so we have the 90% confidence level, and 10% there is a tolerance level, that is equivalent to 0.10. So our sample should be the n is equal to 10,000 by 1 plus 10,000 into 0.1 square. So the result is 99. So out of 10,000 informations, we have to get the minimum of sample size having total 99 uh, number of informations out of 10,000. So this is the requirement in the different fields. So this is one of the example of the population and sample. Then types of statistical analysis. So there are main three categories are involved in the statistical analysis, that is univariate analysis, bivariate analysis, and multivariate analysis. So what is the univariate analysis? So distribution of data using various measures like mean, median, mode, variance, and standard deviations. These are included in the univariate analysis. So, and in the bivariate analysis, it study the relation between the two variables. So, in the univariate, there is a one variable, which may be the mean, median, mode, variance, and standard deviation. But in the bivariate, it is more than two variables, and examine how change in one variable impact other variable. So, likewise, in the satellite image, how uh, spec how this suppose infrared radiations related to the green bands of the uh, multispectral image. So they have different characteristics and the different variables are there. So some of the example of the bivariate is correlation, scatter plots, simple linear regressions. So these are the some of the example of the bivariate analysis. Then multivariate analysis, it seeks the study of relation between the more than two variables. If there is a more than two variable, then we take it as a multivariate analysis. So one of the example is the principal component analysis. It is called as PCA. So if the multi-dimension, if different components of one features are calculated like PC1, PC2, PC3 in different dimensions, then 12, 10 dimension, 12 dimensions. So the features behave in a different ways. So these are calculated in different dimensions. So it is a multivariate analysis. So univariate, bivariate, and multivariate. So these are the example. That is one variant, so, plotted in the box plot and in the different histogram. Then bivariant is in the correlation scatter plots. Then multivariant is in the PC analysis. So type of image statistics. So generally in the remote sensing, the probability distribution function of the brightness level of a particular image or density function of the brightness level of the same image can be calculated, because we have only information about the brightness level and
Hello. Hello.
So now it is visible.
It is visible, sir, but I think we lost connection at some point
Yes, yes,
when you were
some
explaining
internet
about.
connection is lost. Okay, tell me. Hello, hello.
You were saying about uh, I think the parameters of the image statistics. If
Yes,
can I request you to go back to the previous slide, sir? I just would like to confirm where the signal got lost. Okay, this
I
we did.
think.
This
Okay,
we
okay,
did. I think next slide onwards, we were not able to get.
okay, okay. So this so some of them in the digital image that mainly deals with the probability distribution and in the brightness level. So generally the DN values of the satellite image in the pixels or it is a reflectance values. So reflectance values are called as the DN values, and it is a digital number based on the um, the satellite data of different beat, suppose 8 bits, so its maximum value is 2 to the power 8. That means it is maximum value is 255 from 0 to 255. So if the reflectance is high, then the value is maximum 255. If the absorption is high and it will look like the black in the satellite image, then its DN value is 0 to 5 or 0 to 10. So these are the DN values which are arranged in the matrix level, that is in the matrix way, that is row and column. All DN values are in the row and column. So these row and columns are calculated just like the in the statistical analysis, like mean, median, mode. So if we say in the remote sensing it is the mean median mode, it means the value of the mean median mode are the digital number or the reflectance value of the satellite image. So for uh, estimation of different calculation or giving the brightness to the satellite image, so different mean median mode of statistical analysis are calculated. So this is the mean. The formula is the sum of all pixel values by number of pixels. So we have already known about this mean formula. So why it is used in remote sensing that measures the average brightness of bands and areas. So suppose the mean value give 12 or 13. So the average brightness of this satellite image shows that, so it is very near to the absorption capability of the main areas. So basically it is related to the water areas. So if mean value is very high, then the different structures and different high reflectance informations are there. If it is very low, then it may be the water bodies or any forest areas in this satellite image. So mean describes the different informations, and it also gives some ideas about the particular scene of the satellite image. So this is the use of this mean. Then median, it is the middle value and all pixel values are arranged in order. And so this is the calculation even and for odd number. So if the 3 into 3 windows is there from band 4 image, so value in the list is 12, 12 to 16. So this is the matrix of different digital number of different reflectance informations. So generally satellite image has lot of matrix. So it is a one example that it is a 3 into 3 window. But in the satellite image, one scene has lot of rows and lot of columns are there. Like more than thousand and more than thousand columns and rows are there, because each pixel is very small area. So for example, we just take 3 into 3 windows. So just sum all this, and then we calculate the mean. So the pixel is 14.6. So this is the main calculations. And for more, so maximum highest value is calculated. So it is 18. Like this, we'll calculate the median mean mode. So for median, that is arranged in the in increasing order from 12 to 18. So in the median, that is a 15 is the median value. So this is same process. Then mode also, there is the mode that is most frequently use of the digital number. So 15 is more frequently used. That is, there are 3 times 15 information is there. So mode is the highest frequency information. So mean, median, or mode are there. So what is the interpretation in the remote sensing, this mean and median mode? So mean tells average brightness of all the satellite image, useful for vegetation index and normalizations. So most of the time in the vegetation information, so what is the mean reflectance value, we know for different calculation. Then median is for outliers, so good for salt and pepper noise filtering. So what is the median value? So based on this, we will calculate different filtering techniques are there. Then mode reflects the dominant surface features useful in the classification and thresholding. Suppose in the particular area there is a lot of forest areas, and then the mode is for small for particular reflectance, the vegetation information is suppose 100 to 112. So if it is repeatedly available, then we know that it is not a water bodies and it is a forest areas or other areas. If reflectance value, the median value is more than 200, then we know that it is a any artificial structure or any concrete structure is there. So this mean media mode give different information about the satellite image without seeing this image, and these are very much useful in the remote sensing application. Then measure of dispersion is there. So it is generally the understand the distribution of the image data. In other words, it gives information on how stretched and squeezed the values are around their central values. So if it is bending towards one-sided, or it is equally distributed, or particular value is concentrated in particular areas. So how the distribution is present all over the different, all over the dimension of the particular area. So it is calculated based on the different range, variance, and other factors are there. So range is the simplest measure of dispersion, that is calculated the difference between the maximum and minimum values. So maximum DN value, that is digital number, and minimum digital number values. So suppose there is a high reflectance information are there in the satellite image, that is 250, and lowest is that is 5. Then the difference is 250 to 5, then 245. The range is very high. That means it has the information about the object that has some high absorption quality, like the water bodies are there, any wetlands are there. Then also it has also high reflectance, like different artificial structures are there, and some dry lands. And in the dry land also there is a high reflectance. In the salt areas also very high reflectance. In the sandy area also very high reflectance. So these type of features may be present. So this is the basic information we have known. So the large range means there is a both very dark, that is water bodies, and very bright, that is bare soil on any sandy areas are present. So these are the information. So basically anyone can know that if the highest and low information is the width in the wide area is present, then it may be the river or near the coastal areas. So range give different information about the scene. So this is one of the example. This is the satellite image. So it has some brightness values. So it has some brightness value of different high values, are the high DN values are there in the white areas, and same area that has some dark values are there. So it has the very high range. So this is the range. This is the function of the range in the remote sensing. Then variance, one another measure of dispersion, that is measure how spread out the pixel values are from the mean reflectance values. Higher variance means more variability in the pixels and brightness values and indicating heterogeneous surface. So if there is a only only white patches are there in the satellite image, then there is a low variance image. If there are different patterns are there from black, and there is a high level of gray values are there from black to white brightness, then these have the a lot of variance is there. If lot of variance is there, then lot of features are there in the particular scene of the satellite image. So variance give the information about the statistical information and the spatial information of the image, that it is a lot of features are there, like some scene have some dimension of this satellite image have some water bodies, sand areas, built up lands, then forest area, then agricultural lands, then wetlands are there. So if all these are there, then there is the highest variance is found. So this is the one of the formula, that is sigma square is a summation from I to n, that is xi minus mu square by n, where xi is the pixel value, satellite pixel value, which is in the form of reflectance, and mu is the mean pixel value, and n is the total number of pixels. This is, we can calculate the variance, and all the informations are found, all the pixel values, mean pixel values, total number of pixel in image processing softwares. We can calculate all the information about one satellite image. Then suppose one of the example is, suppose that let's take a 5 pixel example of the Landsat in non-near infrared band with pixel values 45, 50, 55, then 60, 80. Then mean is mu is equal to 58. So mean of this pixel is 58. Then difference square is 45 minus mean, that is 169. Then 50 minus 58 is equal to 64. 55 minus 58 is equal to 9. 60 minus 58 square is equal to 4. So in this, the square is indicating there is no negative value for this information, so that square is very much important. Then 82 by 85, there is a T for 84. So variance is equal to sigma square is equal to 169 plus 64, 9, 4, 8, 4, 85, 84, then divide by 5. So there are 5 pixels, so divide by 5. Then 730 by 5, that is 146. So the variance is 146. It means if 0 to 255, so 146 means it's a high variance, and meaning there is substantial variance in pixel reflectance, likely mixed land cover types, water, vegetation, and where, so like all this, all other features are also there. Then standard deviation, so it is a variance. Then the standard deviation, The standard deviation is the square root of the variance. So if the variance is 156, then standard deviation is square root of 146. So in this, suppose we calculate the standard deviation, then its value is near to 12.08. So how in the we interpret this in remote sensing? The low standard deviation means uniform surface, and that example, that is a dense forest or any calm water. So there's a uniform surface, particular scene, a lot of area is dominating particular features like dense forest, or water bodies, or any dam, or is any reservoir is there. And high standard deviation means that very surface reflectance, like urban areas, mixed farming. So this give the high standard deviations. So this is the some of the difference, that is range, variance, and standard deviations. So what tells about the image in the range, variance, and standard deviation? So in range, it is a quick measure of brightness spread. It's a simple thing. Then variance is overall variability in the reflectance of the image. Then standard deviation is variability in the same unit reflectance. So different applications are like in the range is image enhancement, contrast stretching is used in the range. Then after knowing the variance, then length cover heterogeneity analysis also there. Then standard deviation, there is thresholding, change detections of different particular images. So in this scene, I just seen that this is a panchromatic, that is a black and white satellite image of a urban area. So in this area, there's a small dimension, small part of this image are highlighted. That is 5 into 5 pixel is there. So in this pixel, there is a totally black area, and some brightness values are there, and some gray values are there. So generally brightness value give the lowest information, like 15 is the informations, and the brightness value give the highest informations of the reflectance. Likewise, these are arranged in the pixels, like a row and column, all the informations. Then histogram, so it is a distribution provide information of the shape, symmetry, and concentration of individual data. So how this is distributed. So it is like the skewness, like skewness measure the asymmetry of the pixel value distributions. So how it is distributed, like positive skew that deals with the long tail towards the higher DN values, and negative skew that is long tail towards lower DN values. So skewness, this is the formula where x is equal to pixel value, xi is equal to pixel value, then x bar is the mean, then sigma is the standard deviations, and n is the number of pixels. So skewness is the 1 is to n summation xi minus x bars q divided by sigma q. This is the one of the formula. So in the remote sensing perspective, how it is used, if a near infrared band of a vegetation rich area has mostly high DN values, because vegetation reflects strongly in the near infrared, like evergreen forest and mangrove forest, they have they have the high DN values in the near infrared. Then histogram may be negatively skews. Most pixels are bright and with a tail towards the dark sides. So this is the positive skews, and this is the symmetrical distributions of the informations are distributed in very symmetrical ways. Then this is the negative skews. So tail is towards the right in the positive, and tail is towards the left, left in the negative skews. Just remember all these informations. Then kurtosis is one of the peakness of the pixel value distributions. It tells how much of variance due to extreme values or tells compared to the normal distribution. So there are three type of uh, variables are there, that is leptocortic and mesocortic and platycortic. That is, it is greater than, first is greater than 3, and second is the equal to 3, then last is less than 3. So these are like this skewness, but it is in the one uh, areas. So this is the formula. So the difference is only the power is the 4, and this is, suppose this is a matrix of this pixel, then mean value is suppose 21, then histogram would show most values between 12 to 19, but one value of brightness pixel is 100. So this is the one of the pixel which give the most uh, highest informations. So positive skew that tells towards the bright sides, and high QTC because of the extreme outlier in the tail. Why they matter in remote sensing? So skewness help detect bias in the brightness distribution, useful in radiometric normalizations, and QTCs can reveal whether the image has extreme values or not. So useful in cloud detection. So what has sometime due to the cloud there is a high reflectance in getting. So this is also give the information that there is some error in the satellite image. So anomaly detections, and when checking if DN will allow normal distribution before classifications. So this is the skewness versus kurtosis. So this is the mean median mode, and left skewed, right skewed, and normal distributions. And this is the three type of kurtosis are there. Then multivariate image statistics, and in this remote sensing, it is also important to measure how much radiant energy is emitted or reflected back. So to the measure of multivariate image statistic among the band, this allow us to know how the measurement is covered. So we'll go one by one. So first is covariance in remote sensing. So covariance measures how much two variables change together. In remote sensing, we often use to see how two spectral bands are related in term of pixels, different pixel values. So covariance xy, there's the formula. This is a summation from 1 to n, then xi minus x bar into y I minus y bar divided by n minus 1, where x is equal to pixel values in band 1, y is the pixel value in band 2. So basically, it compare the different variables of different bands. So we use the different bands information in the covariance. So what we interpret in this result of the covariance. So positive covariance means the both bands increase and decrease together, and negative covariance means one band increases when the other decreases. That means it is a inversely proportional to the pixel information. Then near zero, there is no relationships. The covariance is near to zero. There is no relationship between the tools. So example in remote sensing, that is if you take band 3 red band and band 4 near infrared band from Landsat satellite image and calculate the covariance, then the covariance is 1200. The value is suppose 1200. So that means it's a strong positive relations. So vegetative areas tend to be bright in both the red bands and in the near infrared bands, and throw with different intensities. So why this covariance is very high in the red and infrared? Because in the both bands the vegetation reflect the more in high the vegetation reflect the high informations, high digital numbers. So this the covariance is very high. Then correlation in remote sensing. So correlation is the normalized form of covariance and give the dimensionless measure between -1 to 1. So this is the formula. Covariance is equal to covariance xy by sigma x into sigma y. So sigma x standard deviation of band x and sigma y is the standard deviation of band y. So how you interpret this? So if the value is plus 1, then it's a perfect positive correlation, and if its value is -1, then it's perfect negative correlation, and if its value is near to 0, there is no correlation. So this is some of the example in the remote sensing for the same band. Suppose that the 3 and 4 bands, that is red and infrared, covariance is 1200, then standard deviation of band 3 is equal to 80 and band 4 is 150. So the correlation is 0.10. It's a very weak correlation in this subset, likely due to the mixed land cover. So if there is a mixed land cover, not the single land cover like forest area or any river or any reservoir is there, then the covariance is correlation is very weak. When you have mixed eigenvalue and spatial direction, that is does not change its direction. So some eigenvalues are there for PCA analysis, principal component analysis. It is spatial direction. So eigenvalue is generally a spatial direction that does not change its direction when the matrix is applied to it, and it only gets stretched and squeezed. The amount of stretching and squeezing is given by the eigenvalue. So, so its direction cannot be changed, but it can be stretched or squeezed. So this stretching amount and squeeze amount is called the eigenvalue. So it is regarded as the lambda v equal to lambda a is equal to lambda v. So it is wrongly written, I think. So it is a lambda x into ax is equal to lambda x. So ax in the ax, there is a n into n matrix. A is the n into n matrix, and this is the eigenvector equal to the eigenvalue lambda and the eigenvector, that is x. So in the remote sensing satellite image, we during the correlation analysis and principal component analysis, we rotate the image in the different dimension to get the different informations. So during the movement of different dimensions, so this eigenvector and eigenvalues are stretched or squeezed. So this amount is calculated. What is the eigen values is there. So it is basically used in the principal component analysis. Then regression in remote sensing. So regression find a mathematical relation between dependent and independent variables. So some is a example is for linear regression formula is y is equal to a plus bx. So this is a variable and there is a constant is there. So y is equal to a plus bx. So where y is a dependent variable and x is a independent variable, and a is a intercept and b is a slope. So in the y section, that is a vegetation index or biomass, and then x independent variable like spectral band and values, because different length to length cover have different and go through the different spectral bands. So if there is no direct dependent and independent variable, so we'll analysis with the regression formulas. So nowadays there is a source line change analysis. That a DCES model is there. So in this model, there is a change in source line for last 2 or 3 decades can be calculated. So in this calculation of the source line change, we similarly we use the regression model. So this DCES model is based on the regression analysis. A lot of techniques are
So
there.
how do we spell source line and defect model?
Digital source line analysis, DSAS, DSAS. So it is freely available in USGS site. we can just give the data of different source line of 2000, 2020 and 1990. Then it give the source line change analysis details of the source line change. And nowadays there is another model is also provided by DSS, that is 5.0 I think. So it also predict the future source line change model. So it is basically integrated with the RGS software. I think 10.5 onwards, the model, the version of the RGS is 10.5 onwards. So you can download and just check how this is accurate or not. So basically, we have to take the different satellite image for analysis of different source line. So basically, we have to draw different source line of different year. Then we give the information about all this, and some technicalities are there, some format are there. So based on their format, we just give it. Then they give the it give the information about the source line change analysis. I have
What is the
prepared.
meaning of soul line, sir?
Soul line means it is a line. It is a line between the ocean and the land part. So soul line is the coastline. So the meeting
Okay,
point
okay,
of
okay, got it, got it.
land and
Okay, okay,
ocean.
got it. Okay, got it.
Okay. So likewise, a lot of regression analysis are used in different applications. So suppose there is a in remote sensing, suppose leaf area index for vegetation on NDVI calculation. There is a uh, so leaf area index is equal to 0.5 into 3.2 into near infrared reflectance. So this is the formula for leaf area index calculations. And if near infrared reflectance is 0.25, then leaf area index can be 0.5 plus 3.2 into 0.25 is equal to 1.3. So this is the value of leaf area reflectance. So this is the regression model, and so it is a one pixel information. So in our different tools are there in our GIS software. So they calculate all this pixel information and then give the leaf area index. When several bands are used, so based on this, then this multiple regression like A plus B1 x1 then B2 x2 instead of A plus Bx. So this is used for crop yield, water quality, soil moisture estimations, and soil line change analysis. So this is the shift of soil line change from baseline. So this type of regression models are used. So this is the 1992 2020 data are there in the soil line interval of 5 years of interval. So it gives the different shift of the soil line from 90 to 2020 to 20. So based on the regression model, we can use the soil line information. So this is the different histogram of different bands like band 1, band 2, band 3 and band 4 of different satellite images. So each bands have different histogram informations. Then this is the covariance matrix and this is the correlation matrix of this. So it is a correlated, highly correlated in the diagonal values are there. Then the principal component analysis is there. Then PCI is remote sensing. So generally, most of the time in the hyperspectral image, the principal component analysis are calculated because it has a lot of spectral bands are there. So due to the presence of lot of spectral bands, we just create one PC1, principal component 1, principal component 2 for different bands. Then correlate all these bands and how one features is look like in one dimension and in different PCA dimensions. So these are correlated. So it is a three-dimensional calculations, and suppose the steps of the PCA in the remote sensing, that is some collect the data in the matrix like pixels and bands, then calculate the covariance matrix between the bands, then find eigenvalues and eigenvector of the covariance matrix, then order component by eigenvalues, variance explained, then transform original data, new principal components. So we have to only give the data, then it automatically calculate the PCA. So generally PCA 1, PCA 2, PCA 3, PCA 4, lot of principal component analysis are there. So each component are given in different ways. So different components of different dimensions are created. So basically hyperspectral remote sensing and multispectral remote sensing also it is used. So suppose Landsat 8 has 7 reflectance bands and many are correlated blue, green, red. So suppose PC1, that is principal component 1, is 80% variance. So it is brightness information, give the brightness information. Then PC2, that is a 10% variance, that is the vegetation and soil contrast. And PC3, that is a 5% variance, that is moisture content. So in suppose in the different 2D dimensions, we get the one information about the object in a particular dimensions, but if create a different dimensions, then the relationships are changes, and we that give the different informations in different component of the principal component analysis. So applications are like data compression, change detection, vegetation analysis. So this is the principal component analysis. So all these data pixel informations are looks like the dots or points and different colors. So suppose we move the one dimension to different dimension, then their positions are changes. Their pixel information, their pixel position are changes, and they give the different informations. So some of the data which are darker in nature in one dimension, if we create a different principal component, then it gives some of the good informations. So this is the satellite image of 8 image. So first principal component analysis give the this type of information, then second is different, then third is different. So in the third information, all the area is black and some white patches are uh, created. So this white patches may be some good information about a particular features. So this can be calculated with the different dimensions. So lot of informations are extracted with the help of principal component analysis, and most of the time hyperspectral in remote sensing is used the principal component analysis due to the presence of a lot of spectral bands are there. So this is some remote sensing based covariance, correlation, regression, and PCA. So, so the covariance is generally of two bands is calculated, and this is the formula. And for example, this is a 1200 of the same value. Then normalized covariance relationship strength, that is 0.1 for a same image, and regression model, that is y is equal to a plus bx, that is leaf area index of a particular area of the same satellite image, that is 0.5 plus 3.2 plus near infrared. Then PCA of different image is different, and for different component is different. For first PCA, PC1 is giving the brightness, then PC2 giving the vegetation contrast. Likewise, different informations uh, we can use in principal component analysis. So most of the time, different PCA not give the accurate informations. So we have to just check whether it is giving the true information for our work or not. So likewise, all these statistical analysis are there in the remote sensing technology. So in the mathematics, they are using the different thing, but same formulas are used for the pixel level informations, and for this, it is very much useful for our different applicable and different applications like different indices and the calculation of different machine learning technologies are there, different models are there. So uh, this is the basic things about the remote sensing and the pixel information. So we have to know the basic information, the basic statistics of the remote sensing technology and the pixel based informations are how they arrange in different statistical based method. So this is the thing about some image statistics. And next class we will discuss the radiometric statistical analysis and other features are there. So is there any doubt? Then we will discuss this. Okay. अभिमन्यु अरोरा जी बोलिए.
So
Hello.
yeah, uh, what we saw earlier, the image statistics was focused on grayscale images, right? So,
Yes, just like grid, and it has the row and columns. So large rows and large columns are there because lot of pixels are there. So basically, all the values are based on the reflectance value in the multispectral sensor and backscatter information in the microwave region. So it is very much important to know the statistics of the remote sensing uh, satellite pixels information. So in the book also very briefly describe all this information. So during practical we will use all these parameters and use the different statistics. So that time all these information are used like PCA regression analysis and all supervised and
so
unsupervised classes.
for
Yes,
multi-band images, then there will be different image statistics for each of the bands, right? Like
yes.
kurtosis
Because
would be different.
each band have different reflectance information.
Yes, thank
That's why we calculate the band ratio. So each band have different information. So if one band and two bands are different reflectance value, then we calculate the ratio. Then it give the different result. So this result can be useful for different purpose, not for all purpose. We will discuss all this band ratio, what is the radiometric resolution in the next class. Okay.
thank you, thank you very much.
Okay. Thank you. And tomorrow we'll meet at 6:30 p.m. Thank you.